So I'm going to write the question down again so we can better understand it. Okay, so here we go. This was the first charge. This was the second charge. And I think the first one was positive. The second one was negative. This is plus. This is minus. This was plus 10 microcoulombs. This was minus 5 microcoulombs. And we had a point A and we had a point B. Now, the question is really similar to the last question, except this time we have a 20 centimeters here and 5 centimeters here and a 5 centimeters here. Now, 5 centimeters is the same. We had this before, but now we have a 20 centimeters here. All right. So what answer did you guys get for this question? Can you guys please share your answers in the chat so I would know what is the answer deviation? All right, send me your answers in the chat so I can look at them. Like the final answer, which is the work done to move a charge from A to B. Yeah, so I did not mention this charge. This is a 5 nanocoulomb charge and we're moving it from A to B. So work done in moving from A to B. All right, now send me your answers. So you solved it till W. Okay, that's fine. Legina's answer is 2.25 into 10 raised to the power minus 6. Okay, I need other answers. Come on, guys. Do we have one answer? I need to see other people's answers. If you have not solved the question, just tell me in the chat so I would know. All right? So come on, send me the answers in the chat so I could compare them and I could see if you guys were on the right track. I want to see where you guys, made the mistake. All right, do we really have no more answers? All right, I'm gonna ask somebody from the class. Okay, so we have an answer from Magina. Okay, so Aisha Iqbal, do you have an answer for this question? Aisha Iqbal, can you hear me? Okay, not bad. All right, we have another 2.25 into 10 to the power minus 6. Okay, that's great. Anyway, so the answers I have right now are both similar, so there's more chance for it to be the right answer. But let's see how we solve this question. Now, the method, you already know the method, right? So you want to find the potential at A, and then you want to find the potential at B. Because we know that work done is VQ, right? And this V, it's not the potential, it's the potential difference, right? So you want to find the potential difference in moving from A to B. If you did all of this, then you're on the right track. So that's amazing if you did this. But if you didn't, now you know what you're supposed to do. Anyway, what is the potential at A? So find the potential at A due to the positive charge, and then find the potential at A due to the negative charge. And when you add them up, they're technically going to subtract, and you would end up with this potential minus this potential at point A. You were supposed to use KQ divided by R, and you would have an answer. All right, does anyone, okay, so minus 900. Okay, so 900, that's most likely the right one. 900. Okay, I might want to recheck that. All right, let's just check it again because, yeah, just to ensure if it's the right one. So 9 into 10 to the power 9 into 10 into 10 to the power minus 6 divided by, all right, so the only way you may make a mistake here is if you don't convert the centimeters into meters. So I believe this is 5 centimeters, which is 5 into 10 to the power minus 2. If you did this, then most likely it's right. And you want to subtract this with 9 into 10 to the power 9 multiplied by 5 into 10 to the power minus 6 divided by 5 into 10 to the power minus 2. All right, so I have the calculator, and I'm going to try to solve it real quick. If you guys have the calculator, do solve it too. Okay. So let's see what answer I get there. Okay, so Legina says there were 5 nanocoulombs. All right, I see. Okay, so the actual question was for microcoulombs, but if I actually wrote nanocoulombs there, then I would like to apologize. Then that's correct. That's fine. Okay, that's great. So if you would have done this question with microcoulombs, your answer would be around 9 into 10 to the power 5. That's why the answers are different. Anyway, let's do this for nanocoulombs, since that's what I wrote yesterday. Okay, VA is 900, and VB follow the same process, and I think the answer should be around, what's the answer for potential at B? Does anyone have the potential at B? Okay, 450. Thanks for sharing. Yeah, 450. All right, then you want to subtract them, and you would end up with 450. That's your potential difference. And work done is going to be 450 into 5 into 10 to the power minus 9. And you would end up with the answer you guys have. So 45 into, 450 into 5 into 10 to the power minus 9. And you would end up with, yeah, your answers are right. Great job. So 2.25 into 10 to the power 6 joules. That's your answer. All right, so good job for those who were able to solve it correctly. And for those who are not able to, if you have any confusion, you can ask me. And yeah, are you guys with me? Does everything make sense? Can we move on? Does anyone have a confusion? Even if you have like a silly confusion, you can ask it right now, because I'm about to move on to the next concept. All right, yeah, Aisha, it must be a calculation error, but I'm glad you got it. Okay, so I'm about to move on. All right, so I'm clearing this, and how can we decide the question? Oh, what do you mean by that? I mean, yeah, what do you mean by how can we decide the question? Oh, the charge. All right. So actually, this charge was, okay, this charge was mentioned in the question, right? This was mentioned in the question. We cannot just, randomly plug in 5 nanocoulombs. It was mentioned in the question, right? So yeah, I hope this makes sense. Anyway, let's move on to the last concept. This is the last concept of electric fields, and it's the easiest concept, honestly. Closest approach. All right, we're gonna have a golden nucleus right here. All right, that's not a circle. Okay, we have a golden nucleus right here. Gold nucleus, right? Gold nucleus. And random values 290, 92, right? Now we have an alpha particle moving towards this nucleus. I know it's kind of weird. We suddenly jump from electricity to radioactivity kind of thing, nuclear physics, but this is also part of electric fields. Anyway, so when when the alpha particle is moving towards the nucleus, what do you think is going to happen? It's going to have some kind of velocity, right? It's going to have some kind of kinetic energy. So can I say that when this alpha particle moves towards the gold nucleus, it loses kinetic energy, right? It loses kinetic energy. All right, so it loses kinetic energy. What does that mean? That means that at the beginning, at the start, I had lots of kinetic energy. My kinetic energy was max. So at the beginning, let's say this is point A, I had the max kinetic energy, like the maximum. And you know that there's going to be a point here where I'm going to lose all of that kinetic energy. So if I have a max here, then obviously I'm going to have a min here. Now there's a little fun fact that I have to share with you guys. Now, when you imagine this situation, you would probably think that, okay, So this alpha particle is moving towards the left, and there's obviously going to be a point where this alpha particle collides with the nucleus. But the thing is, that's not going to happen. This alpha particle will never be able to get to the nucleus. It will stop somewhere near the nucleus. Let's say this is the point, that's the point B. And this is where it's going to have like no more motion. That's where it's going to stop. By the way, what is my kinetic energy going to be at point B? You guys listen to the whole situation. What do you think? What is going to be my kinetic energy at point B? Exactly, it's going to be 0. Kinetic energy is going to be 0. But since this is a nucleus and I have an alpha particle and it's moving towards the nucleus, normally if this was a satellite and if this was a planet, I would say that I am gaining some kind of, okay, I'm not gaining, I'm basically losing. But over here, I would be gaining electric potential energy. All right, so space was not a good example because here it's a bit different. For space, it's reversed. If we move away from the planet, we would gain GPE, right? But here it's different. So here, when we're moving closer to the nucleus, we lose kinetic energy, but we gain electric potential energy. Now, where did electricity come from? Well, that's because of this. All right, by the way, what is an alpha particle? What atom is it? Does anyone know? Basic physics, I think O-level and maybe AS. What is an alpha particle? What atom represents an alpha particle? Does anyone know? Exactly, I'm glad you guys know that. So it's the helium nucleus. And I know that helium has a mass number of 4 and it has a proton number of 2. So I can say that it's going to have some kind of charge, right? Let me explain how. This means we have 2 protons, right? And we know that the charge on one proton has a specific value, which I'm going to share later on, but we have a charge of 2 plus, 2 positive. That's our charge. This means that we have some kind of charge here, and there's obviously going to be some kind of charge here as well. And that's why we basically gain the electric potential energy. But we don't really care about why we gain it. We care about how we gain it, what happens here. Anyway, now, how close we are to the nucleus, it doesn't matter because we never touch it. So that's why this is called closest approach. The fact that we never touch this nucleus, but there's a point that's the closest to the nucleus and we stop there. And that's why it's called the closest approach, because this point is the closest point where we can get to the nucleus. Anyway, let's write the formula for kinetic energy and for this one, but let's start with electric potential energy first. So electric potential energy, just like I mentioned before, it's the same as the work done. So I can say that EPE is just like work done, VQ. V is my potential and charge is, it is the charge. So I know that V is KQ divided by R. But I have another Q here. What does it mean? Does it mean it's going to get squared? No, it's not going to get squared. These are 2 different charges. It's going to be 1, and this one is going to be 2 because we have 2 charges. Now we're going to end up with this formula, KQ1, Q2 divided by R. That's the formula for energy. Now let's plug it into this equation, and we're going to end up with something different. Yeah, these are different charges because we have 2 charges, right? There's a nucleus here and there's this smaller charge. That's why we have 2 charges. All right, let me show you how. So kinetic energy, let's say we're going to have a number. We know that kinetic energy is 1/2 mv squared, right? So remember this because you may use it later on. But let's say we have some kind of value of loss in kinetic energy. That's going to be in joules. And let's say I want to find the distance, this distance. I want to find this d. What would I do? I would plug in the value of k. This is 92, right? So I'm going to have 92 protons. Now, what is the charge on one proton, by the way? If you don't know, I'm going to tell you anyway. But does anyone know? what is the charge on one proton? Does anyone know? Exactly. That's the charge on one proton. So that's also the value of E, and that's also the value of the charge on one proton. So it's going to be 2 into 1.6 into 10 to the power minus 19. Now, this charge is for the helium nucleus. Why? Because it has two protons, right? So it's going to have a charge of 2 plus. So I'm just going to multiply 1.6 into 10 to the power minus 19 by 2, and I'm going to end up with Q1 or Q2. It doesn't really matter which Q is which because both of these are capital, but it's completely your choice. But just make sure that you plug in this Q here and this Q here. Now we're going to multiply this with the second Q. By the way, what is the charge on the second nucleus? Does anyone know? I mean, the nucleus. Does anyone know what's the charge on the nucleus? What is my charge on the nucleus? The charge on helium or alpha was 2 plus. So I multiplied 2 by 1.6 into 10 raised to the power minus 19. Now I'm asking you guys to tell me in the chat, what is the charge on gold nucleus? I mean, come on, it's right in front of you. What do I write here? I'm going to multiply this by the value of E, but what do I write here? Exactly, it's 92. Come on, I even circled it. It's going to be 92. All right, and then we're going to divide this by the radius or by the distance. And this distance, this is going to be that distance of closest approach, a point where we stop. That's going to be the D, the distance between the gold nucleus and the alpha particle. All right, I hope all of it made sense. Uh, Note this down. Meanwhile, I'm going to tell you what kind of questions they can ask here. If anyone has a question, you can ask me. This is like, I think personally, this is one of the easiest concepts in the whole chapter. All right, I'm gonna minimize this and move it here. No problem, I'm not erasing it. All right, so this distance is basically the distance between the nucleus and the alpha particle at point B. Oh, just a second. Let me explain it like this. All right, let me move this over here. It's not moving. Just a second. All right, let's move it over here. And let's move this over here. Okay, and let's divide this by D. All right. Now, what formula am I using? I am using this formula. Loss in kinetic energy is equal to gain in electric potential energy. So let's say I am talking about point B. So D or R is the distance between the gold nucleus and helium or alpha particle at point B, or any point which you choose for this thing. Loss in kinetic energy is equal to gain in electric potential energy. In this case, it's going to be this. Why? Because, yeah, because this is the distance between the nucleus and the alpha particle. Actually, no, it's not that distance. All right, note this down, and if anyone has a confusion, you can ask me. No problem. All right, that's great. So one of the ways in which they can ask you a question is find the initial velocity at this point or something like that. Let's say you have 1 over 2 mv squared, right? And you have the gain in EPE. They can ask you to find the V, they can ask you to find the D, or literally any one of these, I mean, constants. They can ask you what's the charge, etc. So be ready for those kinds of questions. And to get the exposure, make sure you solve all the questions which I'm going to send in this weekend. Anyway, so I'm going to stop the screen sharing and we're going to start the capacitors finally. So give me a second. I'm going to open some images and then we're going to start. All right, so I finally found the picture. I am going to share the desktop. So let's move it and let's full screen it. Okay, I hope you guys can see this picture. And usually we're not really supposed to tell you what capacitors are because this is A level and we care about all those concepts. But I really like for us to understand what are capacitors. Now, for those who are doing A levels, A2 for the first time, you would be surprised by this term because you have never really heard about it before, like never. I'm sure you can see these complicated thingies on my screen right now. Well, if anyone here has ever opened a circuit like, I don't know, like a broken electronic device, you would find all kinds of components. Now, you're not really supposed to know which one of these are capacitors, but all of these are capacitors, and there's different types of capacitors. Like these, for example, you can find a lot of these in toys, like even a walkie-talkie toy or something like that. And these are called electrolytic capacitors. And fun fact, capacitors play a very huge role in FM transmission, like FM radio. There's going to be a chapter called communications really soon, like in the future. And I'm going to mention this concept over there as well. All right. So has anyone ever seen these things or you're literally seeing this for the first time? Yeah, so it seems some of you are like really confused. But as I said, you're not really supposed to know what these are. That's actually great. So these are capacitors. So I just wanted to make sure that you know what you are studying. And we're going to be learning all about them. Just like we studied about resistors back in the day in AS, resistors. Now the diagram, the symbol for capacitor is literally this. You're not supposed to note down anything yet. When I turn on the whiteboard, then start noting it down. So this is a symbol of a capacitor, right? And you know that this was a symbol of a resistor. So a resistor is represented like this in A level. In reality, it's represented like this. And it turns out that capacitors are also represented in a different way. So let's say this capacitor, for example, it's represented like this because it's an electrolytic capacitor. But then again, we're not supposed to learn that. Anyway, so this is the symbol of capacitors, and that's literally all you're supposed to know. This little shape is all you're supposed to know for A-level physics. Now, I would like to explain what are capacitors. Now, these are the more complicated versions of capacitors, but in reality, all of them follow a similar pattern. So we have two pieces of metal. This is a sheet of metal, like a metal plate. These are metal plates and metal plates. And the thing inside there, that's an insulator. So we're not supposed to show that, but there's an insulator. And there's another fun thing. When I apply electricity, let's say I put a battery here, right? There's a battery here. And let's say I apply some kind of current, some kind of voltage, let's say 1.5 V, right? Now, what's going to happen is because this metal plate and this metal plate, because they are separated, they're going to store energy. And that's literally what capacitors are. Now, let's start learning what they are. So this chapter and electric fields are, I mean, they go side by side. So it's always a good idea to learn electricity, electric fields, and capacitors together. Okay, so we have like 9 minutes in this meeting left. I would like to continue this in the next meeting. So we would have uninterrupted 40 minutes. All right. So I'm ending this meeting right now, and I'm going to see you all in the next meeting. I'm sending the link immediately. Continue. All right, now let's start the A-level capacitors. Right, capacitors. Capacitors. Okay, so just as I made it before, these are literally two lines and connected with a wire. That's capacitors. We're literally learning a whole chapter about some cylindrical little components. They're so small, I bet even your finger's not that. I mean, yeah, it can fit on your finger. That's how small it is. Even smaller than that. I think even smaller than the nail, something like that. Anyway, that doesn't matter. So this is called a parallel plate capacitor. Now let's understand what actually happens here. Now, this thing, it stores energy, right? That's all you need to know for now, and we'll see how. So capacitors, they store energy, right? They store energy. That's it. They store energy. And that's why we use them, because they're like small mini batteries or something, but batteries are still something else, and capacitors are different. Anyway, let's make a diagram and let's understand how are they storing energy. So here we have two plates, and this is a little circuit we made. We have a battery here. Let's add a decent sized battery. Let's say this is like 2 cells attached in series, 3 volts, right? Now, there's going to be a current coming out. By the way, just a little fun question for you guys. I have the bigger plate and I have the smaller plate. Which one of these sides is going to emit electrons? Is it going to be A or is it going to be B? Which one of these is going to be the pathway for electrons to flow? Just a basic question to check how good you know physics. Come on, guys. Right, so we have two answers here. Okay, now there's one thing I want you guys to know. There's something called a conventional current, and then there's, I don't know what it's called again, but it's the proper current, the actual electron flow. So if I would ask you what is the direction of conventional current, it would be this. But then I did not really ask you this. I asked you, what is the direction of the electron flow? Now, never forget this thing. The bigger plate is always the positive plate. So this is plus, this is minus, this is plus, and this is minus. And I mean, it's pretty obvious that which one of these is going to be for electrons. So the smaller plate is always going to be the one for electrons to release, right? So electrons are coming from here, they're going to flow up, they're going to go from here, and they're finally going to reach the capacitor. Now, there's something going to happen here. No, Key, listen. Current flow is one flow. This is the current flow, right? This is the actual current flow. But scientists or physicians, they realize that it's actually more convenient for them. It's convenient for them to assume that this is the current flow. So this is called the conventional current. So if I would say that current is coming out from plus, this is called the conventional current, right? So this is the conventional current. This is what is taught to students in O-level because it's just more convenient to do all the formulas, you know, the left-hand rule, et cetera, et cetera. It's easier to assume that the current is flowing from here. But in reality, like the actual reality is that the current is coming out from the negative plate. I think you guys have noticed this in chemistry. In chemistry, we were never told to use the conventional current. We were always taught that, okay, this is the current flow. But in physics, O levels, we were taught that there's a conventional current and then there's another current. So we do not care about this current right now because we need the electron flow, right? So there's two current flows, and the actual current flow is this one. That one is the conventional flow. I hope it made sense. Anyway, now what's going to happen here, these electrons are going to come here, but I mean, where do they go now? There's literally nowhere they can go. So what they do, they start gathering up here, they start storing up here, and they kind of, yeah, they kind of collect over here. Now, what happens here is this thing is called, this is called a dielectric. This insulator is called a dielectric. A dielectric. Maybe insulator is not an appropriate word. This is basically a dielectric. They're separated by a dielectric. And you guys are smart. You know that whenever we have a plus on one side, let me make the pluses a bit big so it's obvious what this is, like minus here, minus here, minus here. Okay, now I have a lot of negative charge here. Doesn't it mean that it's gonna induce a positive charge over here? Don't you think so? Because I have minuses here, I'm gonna end up with plus here. Now, you know what actually happens here? Look, we have, let's say we have, okay, never mind. Basically, we have a lot of electrons here, and because we have a lot of electrons here, and these number of electrons, there are like a lot. That's why it has an overall charge of minus, and since they cannot flow any further, there's going to be a positive charge induced over here. Now, I have a positive charge here. Something is going to happen now. Right, so this is going to become plus Q, and this is going to become minus Q. Right, so the total charge over here is total charge. The total charge is going to be minus Q plus Q. Yeah, so minus Q plus Q, and we're going to end up with 0 coulombs. That's it. Now, I would like to pause over here for a second. A general thing, negative charge here, plus charge here. But I'm going to explain how exactly in a little while. First, we have to understand something here. So let's move it aside. Let's minimize this. Okay, let's minimize this. All right, so work is done to keep the plates apart, and this work is stored in the form of electric energy. Now, we have a plus charge here, and we have a minus charge here. Now, obviously, they tend to attract, right? Because, I mean, plus and minus, but work is done to keep them apart. Work is done to keep them apart. And this work is stored in the form of electric energy. And that's exactly how work is done. That's exactly how energy is stored and not the charge. Now, a logical assumption would be that capacitors store charge. But for those who think it stores charge, there's going to be a question for you in CIEs, right? So this is a CIE question. And they may ask you, why does a capacitor store energy but not charge? And your answer would be this. Work is done to keep the plates apart, and this work is stored in the form of electric energy. Now note it down till this part and tell me once you're done. All right, so while you're noting this down, I'd like to finally explain what I wanted to explain and where I paused here. Look, you guys are supposed to know how exactly we get a plus here. Yes, we have a minus here and then we got a plus here, but how? Look, in the beginning, we had some electrons here, right? At the start, we had some electrons here. Now, when these electrons here, they pile up, they are going to repel these electrons, and these are going to flow to this battery. And because these electrons flow to the battery, there's going to be an overall lack of electrons here, and we are going to end up with a plus charge here. That's how this minus is inducing a plus over here. Okay, so Aima, you mean this question, right? No, you are not supposed to mention dielectric, at least for this question. I will tell you when you're supposed to mention the dielectric. So a short recap, there were some electrons here, right? But since we are getting a lot of electrons here, these are going to push those, and those are going to come back to the battery. And at the end, we're going to end up with a total positive charge over here. And that's how we have a minus here and we have a plus here. No, 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 they're not passing over this region. We had some electrons here, right? We have some electrons here. What's happening is these electrons are pushing those electrons, and those electrons are flowing here, and we end up with a positive charge over here. But if that is very confusing, then just as I mentioned at the beginning, just remember this. Because there's a minus here, we're going to end up with a plus here. But it's obviously preferable that you understand how we get that minus. I'm still going to get back to this, right? Because we're supposed to do something over there right after this. Anyway, no problem. And let's continue. So capacitors store energy, but in what form? So capacitors, I mean, they store energy in joules, but capacitors have different values. So capacitors have this quantity called capacitance. And capacitance is equal to Q divided by V. The units of C are F, the units of Q are C, and the units of V are V. So red ones are the units. Now there's a very interesting confusion that students get when they do the paper. Look, this is the symbol of charge, but it has a unit of coulomb, right? But now we have capacitance, and this is a C again. This is a C2, but this is not coulomb, this is capacitance. And capacitance unit is not coulombs, it's farads, F. So don't get that confusion. So Q is the charge stored in any one plate. So like one plate, not the whole capacitor, right? So that's the charge on one plate. Then we have V, that's the potential difference across the plates. And we have finally the capacitance, and the unit of capacitance is farads, so a capital F. Right, so that's the unit. And they can also mention it in microfarads and millifarads, so be prepared for that as well. All right, I'm about to clear the other side of the whiteboard. In the questions where we're going to find the energy, we have not learned that yet. So I'm going to get back to that. But short answer, no, it's a bit different. Okay, parallel plate capacitor. Let's talk about this. All right, I'm going to move this and let's do this. Okay. So capacitance, another formula for capacitance is this. E naught A divided by D. Just a second. All right. So capacitance. That's E naught A divided by D. What is capacitance? Capacitance is the ability to store charge. Let's make the two plates, and I'm going to show you what is area here and what is D. So the two plates are like this. This is the first plate. This is the second plate. And there's going to be a distance between these two plates, which is D. And obviously the area is going to be A. So this is going to be A, the area. All right, so A is the area of one plate. D is the distance between the plates. Okay, I'm erasing this and all right. Yeah, I read your thing you said here. Capacitors, they store energy, but I'll still confirm this because when my teacher was teaching me, he also mentioned that capacitance is the ability to store charge. But you have a point. Capacitors do store energy, but there's a reason why he mentioned this. So just give me a second. I'll confirm this. Okay, it is indeed electric charge. So yeah. Anyway, I double checked just in case. Capacitors store energy, but capacitance is the ability to store charge. Why? Because we just saw that capacitance is Q divided by V. That's one. Two, when I say that capacitors store energy, imagine this. Energy is being stored between them, right? But capacitance would be the ability to store charge on one plate, let's say, right? So minus, minus, minus. You could say that. So if they give you a question where they ask you, tell us why capacitors store energy but not charge, you would mention that reasoning. But the definition of capacitance, like the official definition, it's not my definition, it's even on the internet, the official physics definition for capacitance is the ability to store electric charge. Okay, I hope that made sense. Now, I would like for you guys to pay attention over here. I know that area, let's say that for a second, I am using the same area of the plates, right? I'm using the same area of the plates. Now, this means that E naught and A is going to be constant. Now, capacitance and distance is going to have an inverse relation, meaning the lesser my distance, the greater my capacitance. The greater my distance, the lesser my capacitance. So strength of an insulator is inversely proportional to capacitance. That's another point which I'd like to share. All right, before that, let's look into this. This is a point charge. We're going to see this phenomena right here again. This is a point charge. I'm not making it as a point, but let's say this is the radius, and this is all of the charge. So for a point charge, V is kq divided by r. But since we're doing it for the sake of definition and not for the sake of calculation, just like I mentioned before, I'm going to use 1 over 4 pi e naught multiplied by q divided by r. And I'm going to end up with this. So capacitance is q divided by V. And I'm going to substitute this into that, and we're going to end up with something over here. Okay. So Q divided by, just give me a second. Let me move this up. Okay, note this down, just give me a second. I have to confirm one thing over here. All right, so basically, we're going to substitute V into this, and we're going to end up with this. Q divided by Q, and again divided by 4 pi e naught r, right? So we plugged in this V into that. So this was our first equation, and then we plugged in this whole potential into this equation, and we ended up with this. Now, I know that QQ are going to get canceled out, right? So finally, I'm going to end up with C is equal to 4 pi E naught R, right? So because it's going to be 1 divided by 1 divided by 4 pi E naught R, at the end of the day, we end up at the end, we end up with this. I hope this made sense. Are you guys with me? Does this derivation make sense? All right, I'm glad. Anyway, so this is what I wanted to prove. There, it was a bit different because we had area, but now it's about a point charge. I know that 4 pi E naught is constant, so I can say that C is directly proportional to the radius. That's a different case. This is a different case. So for a point charge, capacitance would be directly proportional to the radius. Okay, so Pakiza, this is basically K, right? You know that V is KQ divided by R, and K is 1 divided by 4 pi E naught. So let me just write it over here so you don't get confused. So K is 4 pi divided by, oh, what am I doing? It's 1 over 4 pi E naught. K, K is a constant. This is a constant. E naught. Okay, Ima, I think you were not present that day, but no problem. It is the relative permittivity of free space. Listen, K is a constant. This is a constant. This is the electricity constant. So just for you, E is the permittivity, relative permittivity of free space. So in short, this is that thing that decides what force or what electric field our charge is gonna have. Basically, this is what decides how the charges act in different mediums. Just a fun example I mentioned that day, NaCl, sodium chloride. It exists as a solid in air, right? But when we put it in water, it becomes aqueous. Why? because in water, the relative permittivity of free space is different. And that's why the force between the charges, the positive sodium ions and the negative chloride ions, is going to be weaker, and thus they're going to be farther apart. And that's why it ends up as aqueous. Anyway, I'm about to clear this whole thing up. I hope you guys have noted this down. Okay, now this is the real thing which you need to understand now. This is one of the most confusing things, so be prepared. Charging of a capacitor. I'm going to make a circuit here. I have a capacitor here, right? A capacitor here, and I have a circuit. And there's a micro ammeter here. And finally, we have a battery. So this is a battery, and we have a switch. And I have placed a voltmeter in parallel with the capacitor. So this is a 6-volt battery. All right, so initially, at the beginning, the capacitor is going to be uncharged, right? So initially, the capacitor is uncharged, right? So it's not going to have any kind of voltage, right? So at time 0, we're going to talk about this battery, right? So at time 0, the battery, or the potential difference in the circuit is going to be 6 volts, right? So at the beginning, the potential difference is going to be 6 volts. But as the time passes, right, as the time passes, let's say t is equal to, I don't know, 10 seconds, we're going to have 0. Let's go with 100 seconds because 10 seconds is a bit too less. 100 seconds, and we're going to end up with 0 volts. So potential difference decreases. The potential difference decreases. Let that sink in for a second. So in the beginning, my microammeter is going to show me max deflection. Max deflection on ammeter, right? Or voltmeter. So let's go with max deflection. So in the beginning, there's going to be maximum deflection, telling us that the value is the max. Let's go with the voltmeter. So in the beginning, we have max deflection, and we end up with deflection decreasing as the time passes. And at this point, what's actually happening is capacitor is fully charged. So let's say we have, I'll explain, Key. I'll explain. Let's say we have VC of capacitor. So the voltage of capacitor is VC. The voltage, the potential difference in the circuit is 6 volts. So VC is the voltage of capacitor. So VC is going to become 6 volts. Okay, so listen. When you close the switch, we have the maximum potential difference, right? So the ammeter is going to show the it's going to show maximum reading, and the same is true with the potential difference. So in the beginning, we're going to have the maximum reading, and by deflection, I mean that we have maximum reading. So deflection is proportional to the reading. So the larger my reading, the more deflection I have, and as my reading decreases, the deflection decreases. Now let me explain how it's happening. Look, the battery has 6 volts, right? At the beginning, now pay attention here because this is what's going to build your concept. In the beginning, the battery has 6 volts, but the capacitor has 0 volts. But as the time passes, the capacitor is going to get charged. The capacitor is going to get charged. So let's say there comes a point when the battery is, I mean, it's 6 volts as it was before, but now the capacitor is also 6 volts. So let's say this is true for time 100 seconds. Now, what's going to happen? We have 6 volts here, we have 6 volts here. So we're not going to have potential difference at all, right? This is literally the same as 0 volt or 0 volt or 2 volt or 2 volt. Current is not going to flow. If the voltage over here is the same as here, the current is not going to flow. Why does the current flow? Because there's a potential difference, because we had 0 volts at the beginning. That's why the current is flowing, right? That's why it's getting charged. But there comes a point when it gets charged up and we have 6 volts here and we have 6 volts here. What's the result? The current doesn't flow anymore. And that's why we have the minimum deflection. So no deflection. I hope this made sense. If anyone has a confusion, you can ask me. I can literally explain the whole thing again. So do let me know if you have any kind of confusion here. All right, are you guys with me? I know that's a lot of stuff to absorb, but are you guys with me? Okay, I'm glad. What about the rest? Okay, that's a good question. Look, in reality, okay, that's a very smart question, man. That's a nice question. Look, in this example, this is happening. But when we have a circuit, you know why capacitors are used? I don't know if you guys have seen this, but I once literally tore down a Wi-Fi, right? A Wi-Fi, not the Wi-Fi, like the internet modem, and there were a lot of capacitors inside. So when I plugged it in, the LED turned on, telling me that it is on, right? So I plugged it in, the LED is on. Now, it's not gonna happen like this, like it's getting charged up and there's no potential difference, so thus there's no current flow and the light goes off. That's not true. In reality, in the practical world, we use capacitors so they store energy. Let's say suddenly the light goes off. Did you notice that when electricity is off, some devices, they don't turn off immediately? It takes a few seconds, right? It takes a few seconds for it to turn off. That's why capacitors are used, for stability. But obviously capacitors have other uses as well, and we might not talk about this one, but the one that I have noticed is it gives stability. Like, let's say there's some current deviation, but capacitors have that energy. A lot of motors, they have the capacitor on to provide that continuous supply of electricity. I have watched a lot of videos about capacitors on YouTube. I will share those videos with you guys, and it's going to make more sense. So while my knowledge might not be able to comprehend how it all looks like in the bigger real world circuits, but what I can say is that's not how capacitors work in real world. Like, it's not going to happen like this. So like 6 volts, no more current, no more flow. But yes, if I somehow attached a bulb here and if there would be no current flow, then it would not light up. Okay, so I was just reading your messages. I mean, yeah, there must be capacitors in them as well. Okay, so let me show you for a second. Uh, I will have to watch that video again, and you're not really supposed to know this in A level, but we're learning for the sake of learning, right? We're not learning for the sake of robotic learning. Let me make this for a second. Let me try to show that. So look at this. You seem to be interested in the practical physics. That's really nice. So I think the circuit I have seen in the internet. So I hope you guys noted that down. Let's try to make this. And let me show you. I think I might be able to explain this to you. Right. So again, I have not really studied how home circuits work, but I have seen that video and it was a really nice representation of what happens. Let's say this is a bulb, right? And we have a current flow, right? The current is flowing and the capacitor is getting charged, right? And the bulb is also being lit up, right? So the bulb is lit up, right? We have the bulb that's lit up. By the way, you're not supposed to know this. I'm only answering Keith's question, right? So the bulb lights up, and I mean, it lights up, and the capacitor gets that energy, right? Let's say we end up with 6 volts here. Now what's going to happen? Yes, indeed, there's no potential difference here. So the current may not come from here. What's going to happen now is, in that video I saw, you know what they did? They did it like this. So when the switch is on, look at this. When the switch is on, right? When the switch is on, the capacitor gets charged up, right? But now when it's 6 volts, we don't really need the battery anymore. So that's what they do. They turn off this switch, the switch opens up, and now this capacitor provides the electricity for this bulb, right? So this capacitor causes the bulb to remain lit up, and then the process continues. Now it's 0 volts and it closes like this. And again, the capacitor gets the energy, blah, blah, blah. And then finally, this cycle repeats. I hope this makes sense. But I will show you that video. It should make a lot more sense after you watch it, right? So yeah. No, it is discharging. Come on, it is discharging. Look, when I turn off the switch, it is discharging, right? That's how it goes from 6 volts to 0 volts. Don't you think so? Right? All right, so we have 2 minutes left, so that's going to be it for today. I'm just going to answer your questions. If you don't use a capacitor, I mean, what would happen is, let's say this is a Wi-Fi modem or something, just as I mentioned. So if you don't use a capacitor, when you remove this plug, it's immediately going to turn off. Right? So LED is going to turn off immediately. So there's not going to be anything inside that's storing up that charge. I would say that capacitor is also used to lower up the burden of the battery. So if I have a battery here, right? So let me show that again. Okay, if the meeting ends right now, I'm really sorry. I'll continue this tomorrow. But basically, you see we have a capacitor and we have a battery. So the battery doesn't have to work 24/7 anymore, right? The battery can rest. So it reduces the load on the battery as well. That's also one of the things you can say. Okay, Key, if the meeting ends right now, send me your questions in the WhatsApp, right? Okay, it didn't end. Okay, let me answer you. I mean, not all circuits, but most of them have the capacitors, at least your FM radio. Now, capacitors don't only store energy. There's another use for it. Let me show you something really cool, which you're not supposed to know at all, but just for the sake of it, let's say. So there's something, let's say this is my capacitor, right? This is my capacitor, and there's something called an inductor. So let's make the inductor. You're not supposed to know what this is. This is also one of the components. Now, this is the thing that sends that signal that FM transmission needs. I'm going to explain more about it in the next lecture, but capacitors are also used in FM transmitters. They are the cause of this signal to be generated. Anyway, the meeting is ending. Allah Hafiz. Okay, I'll see you guys tomorrow, all right? So Allah Hafiz, guys. The meeting is going to end on its own right now, but I'm ending it before that happens. Bye-bye.